Okay. So no questions. Okay, let me show you what we were doing last time. So we started, so this subspaces we did last week. Okay, so we defined something called subspace, and we defined something called linear combination. Okay, so what is linear combination? Linear combination of vectors. Okay, this capital V stands for vector space. These are the vectors, and these are scalars. If I form a sum like this sum is called a linear combination. Okay, so a linear combination of vectors is a vector because I'm just multiplying vectors by numbers and then adding them, so the result is always another vector. Okay, so then we looked at problems like this. So is a given vector a linear combination of the other vectors? Okay, so vectors can mean different things. For example, if you are in the vector space of matrices, then the vectors are matrices. Okay, so 4.4, this is something called span. So what was the definition of span? So we are given a vector space and some vectors in it. Okay, then we consider a set which is the set of all possible linear combinations of these vectors. Okay, and the resulting set is called the span of these vectors. Okay. So for example, the span of these two vectors in R2, 1, 2, and 2, 4. What is the span of these two vectors? If you look at the span of these two vectors, so the span is really a multiple of this vector 1, 2, right? Because the vector 1, 2 is on this line, and the vector 2, 4 is also on this line. So if we consider the span, all those vectors which can be written as linear combination of these two vectors, they lie on this plane. Okay, so for example, if I take two vectors in R3, then their span will be, oh, what is this? Okay, this is, these two vectors again lie on a line in R3, but these two vectors, they do not lie on a line, and their span is a plane in R3, okay? A plane which passes from the origin. Okay, these are just reminders from what we did yesterday. So we then consider different vector spaces, like the vector space of polynomials, okay? If we looked at the span of these two polynomials, then the span of these two polynomials is all the polynomials in this form, a constant times t plus constant times t squared. Okay, let me skip these things. Okay, let me do one more example and then we go to the next section. This example is kind of important. Let's look at it. Okay, so this is an example. Okay, so for this example, we need a matrix. Okay, so let's look at let this be our matrix. So we have a 4 by 4 matrix for this example. Let me copy it. 1 minus 2 and 1 and 4. Then 1 minus 2, 1, 4, 0, 1, minus 1, and minus 1. And then 2, minus 5, 3, and 9. Okay. So we are considering this equation, 8 times x equals the 0 vector. Okay. So we're looking at the, so remember this is called homogeneous system. So the problem is this: find find a set of vectors which span the solution space. Let's make this smaller. The solution space. Okay, so what do we do? Now we are trying to find the solutions of this system, right? It says find the vectors which span the solution space. So how do we solve this system? This system AX equals 0. So what we do is we write the matrix. Okay. So here I don't want to write it again, and then we put zeros here. 0 is the vector on the right hand side. Then we do row operations. Okay, so for this one, what are the row operations? So we should do, if you look at this, so what we do is we multiply this row by 2 and then add it to this row, and multiply this row by -1 and add it to this row. Multiply this row by -4 and add it to this row. Okay, so let me write it. So 2 row 1 plus row 2 to row 2, and then minus row 1 plus row 3 to row 3, and minus 4 row 1 plus row 4 to row 4. Okay, let's see what happens. So we get the first row does not change. This becomes 0, 0. Then this becomes 1, and this becomes -1 and 0. This is 0, 0, -1. So I multiply with -1, so this is 1. This is 0. And this is 0, 0, -1. What is this? This is 1, 0. Okay, so we get our first leading one. This is our first leading one. And this will be our second leading one. Okay. So what do we do? Okay, we try to make this part 0. Okay, so for that one, what I do is I multiply row 2 by 1 and add it to the third row instead of third row. And I multiply the second row by 1 and add it to the fourth row. So these are the operations. So if we do this, what do we get? So we get 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 2, -1, 0, 0. And here we have just zeros. Okay, so this part is okay. Now let's make this smaller. Okay, now if you look at those equations, what do we find? Okay, remember this first column stands for x1, the second one x2, x3, and x4. So we have 4 components. So this means x1 plus x2 plus 2x4 is 0. And the second equation is x3 minus x4 is 0. Okay, so you see we have only 2 leading ones. So we have leading one here and here. So x1 and x3 have leading ones. but x2 and x4 do not have leading ones. So we will call x3 and x2 and x4 as free variables, okay? So x2 and x4 are free, so I can give x2 the name R, so this is free, and x4 is also free, so we gave the name S. Okay, so these are the free variables. They can be anything. So once I assign these letters to x2 and x4, x3 and x1 are determined. So x3 becomes x4, which is S, and x1 becomes minus R minus 2S, right? Any questions? So we found the solution. Let's write the solution. So what is the solution? Solution is the vector x1, x2, x3, and x4. Okay, so what is x1? x1 is minus R minus 2S, x2 is R, x3 is S, x4 is again S. This is good. So this is the solution. Now it says find vectors which span the solution space. Now this part is, let's look. So I will do a trick here, which is a very important trick. So I will write this solution into two parts. The first part being minus R. So I will look at the part which contains R terms, and I will look at the part which contains the S terms. This is minus 2S, 0, S, and S. So these two vectors are equal, right? So if I add, if I look at this, this plus this equals this, right? Okay, now let's look at the first vector. I can write the first vector as minus 1, 1, 0, and 0. So I took it into R parentheses. And let's look at the other part. Minus 2, 0, 1, 1. Okay, so what is this? What did we find? Okay, what we find is we found the vectors which span the solution space. So this vector, minus 1, 1, 0, 0, and this vector, minus 2, 0, 1, 1, span the solution space, because I can write any solution as this vector times a number plus this vector times number. This is the definition of span. Okay, so these two vectors span the solution space. So this is very important because solution space is infinitely large. There are infinitely many solutions, but you see, just two of these vectors are enough to represent all the solutions. This is a very important idea. There are infinitely many solutions, but only two solutions, only these two solutions are sufficient to write all the solutions down. Okay, so this is that. So let's write this answer. So solution space is the span of these two vectors, minus 1, 1, 0, 0, and minus 2, 0, 1, and 1. Okay, so we talked about the geometric idea behind this. What we find is also the geometric idea is this. So there are two vectors in the four-dimensional space. I cannot draw the four-dimensional space, but there are two vectors corresponding to, so these vectors, okay? One of them is this vector, the other one is this vector, and they form a plane, okay? So solution space is really a plane in the four-dimensional space, okay? So there's a four-dimensional space of solutions, and the solution space is a plane in this four-dimensional space spanned by these two vectors. Okay, so this is the end of this example and this section. Let me know what you think about this section. Do you have, how is your feeling about it? Great, okay. Any questions? Very interesting, okay. I think this is very interesting, yes. So you're kind of abartmayın arkadaşlar. Fascinating, very interesting, great. Okay, sevdiğinizi beğendim. Okay, so so in a sense, you're expressing something complicated in a simple way. Okay, so solution space is something that we cannot visualize, but now we can visualize it. So it's just the span of two vectors. This is a good idea. Mars yapar mısınız bir dahaki derste? Bir dakika ara vermişken hemen sana bir Mars şeyi yapayım ya. Güzel bir Mars bulalım. Okay. Okay, so we have few more sections like this, some theoretical things. And after that, it will be more practical things. But yeah, so. Let me know if you have questions. Okay, so this is the Mars picture. Okay. Let's move to the next section. So section 4 let me see. Section 4 point. Elon Musk mı beğendi bunu? Section 4 point what? 5. Section 4.5. Let me make this bigger. So the name of this section is linear independence. Independence. Okay. So let's remember an example that we did. Okay, so we have seen that. So let's look at this set W, which is all the vectors of this form A, B, and A plus B. Okay, so this is a subset of R3. Okay, which is a subspace. It's not just a subset, but subspace. We have seen that this is a subspace. What does it mean to be a subspace? It means that if I take vectors of this form and add it to vectors of this form, the result will be vectors of this form, which is the sum of the first two components is the third component. okay? And if I do this for scalar multiplication, it's still the same. So a number times a vector of this form is a vector of this form. So this is a subspace. And then we have seen something like this. W is, okay, W is, in fact, it can be written as span of two vectors, span of which vectors? So it's still the same idea. If I take this into A parentheses, I get 1, 0, 1. And I also get, if I take into B parentheses, I get 0, 1, 1. So all the vectors in W can be written as linear combination of these two vectors. Okay? So this is the span. But this is, I can write this W also as span of these maybe three vectors, okay? So once I get these two vectors, I can add any vector I want. Not any vector I want, but for example, if I write also this, okay, so what do I get? So you see the third vector here is really sum of the first two vectors. So in a sense, this third vector is not adding a new information to this span, okay? So these two vectors span a subspace, and adding this third vector gives us no new information about, because this is already a linear combination of these two vectors, okay? Right? So this is still true. Okay, so now there's an idea about this, and it's called linear dependence and independence. So we have this V vector space, and we take some vectors in it. Okay, so these are the vectors. Okay, and we call them linearly dependent. Linearly dependent if there exists scalars, meaning numbers, such that A1, V1, so these are vectors and A1 are A1s are numbers. AK, VK equals 0. Okay, so I can put vector signs. Sometimes I use a vector sign, but sometimes I don't. So, so if there exist scalars, I didn't write this, A1 to AK. Okay, I should there exist scalars. I should say A1 to AK. And there's an important word here, so I have to write it. Not all 0, okay? Not all 0. Okay, now let's look at why that thing is important. So look at this. So we call these vectors linearly independent if there exist scalars not all 0 such that this equation holds. Of course, if I choose A1, A2, AK as 0, then this equation is automatically satisfied. So something I have to fix here. So this 0 is also a vector, right? Because sum of vectors is a vector, not a number. So if I choose the numbers as 0, this is always satisfied. So the important point is whether I can find a non-trivial solution for this equation. If there's a non-trivial solution, then they are called linearly dependent, okay? And if a given set of vectors is not linearly dependent, it is called linearly independent. Let's write it also down. If these vectors are not, or this set is not linearly dependent, let's write linearly dependent like this, then it is called linearly independent, linear bağımsız. Okay, let's look at the previous example. Okay, this one. So let's try to see whether these two vectors are linearly dependent or independent. And let's see whether these three vectors are linearly dependent or independent. Okay, let's first look at these two vectors. So the question is this: is the set? Let me copy this, right? Can I copy it? I think I can copy it. Copy. Okay, is the set? It didn't save too much time, but it's okay. Is the set linearly dependent or independent? So we have two possible answers for it. Either it's linearly dependent or linearly independent, okay? So let's look at the solution. Okay, so we start by writing this equation, which is a1 times the first vector plus a2 times the second vector. And then make it equal to 0 vector. So now we want to solve this for a1 and a2, and we're wondering whether there's a non-trivial solution or not. Okay, so let's, just by inspection though, so the first line tells me a1 is 0, not by inspection, but a1 is 0, and a2 should be 0, and the third line says a1 plus a2 equals 0, right? So if you look at this, let me zoom this. So this means a1 plus a2 equals 0, which means a1 is 0. a1, 0 a1 plus a2 equals 0, which means a2 is 0. And a1 plus a2 is 0. So what is the solution of this system? There's only one solution to this system, which is a1 and a2 being 0, okay? So there's only one solution. This is a1 equals a2 equals 0. There is no other solution, okay? And this solution is the trivial solution, because this always satisfied no matter what vectors these are. So if I multiply them by 0, the result will always be the 0 vector. So this is trivial solution. So what does this mean? Let's go back to the definition. What do you think? Are these vectors linearly dependent or independent? Which one? Independent. Yes. Independent, right? Yeah. So let's look at this writing here. So if there exists scalars, not all zeros. So for linear dependence, you want a non-trivial solution. Okay, so this really means, let me write it in a different color. So this means a non-trivial solution. So if there's a non-trivial solution, then it is linearly dependent. And if it is, if there's only like trivial solution, so not linearly independent means there's only trivial solution. Okay, if there's only trivial solution, then it is linearly independent. So in this case, the answer is the answer will be linearly independent. This is not the Is this the red color that I was using? No. This is my red. So this means linearly independent. Okay? They are not linearly dependent, yes. Okay, so we found that this first set of vectors, these two vectors, is linearly independent. Now let's check these three vectors. Okay, let's look at these three vectors. Example, let me copy this again. So copy, paste. Okay. So the question is the set linearly independent, dependent or independent? Okay, so again, let's look at the solution. So we form this product, which is 101 plus A2 times, what is this? 0, 1, 1. Now I have another vector, so I have to use the symbol A3, which is 1, 1, 1, which equals 0, 0, 0. Okay, now what are the equations? In this case, the equations are A1 plus A3 is 0. Make it smaller. Then A2 plus A3 is 0, the second line. And the third line says A1 plus A2 plus A3 is 0. Now we are looking for the solutions of this. Okay, this is the same problem that we've been doing for all the time, right? So I can write this as a matrix system like this, and then I write the right-hand side, which is zeros, and then do the row operations. So if I do the row operations, what do I get? So let me do this quickly, because we've been doing this for all the time. So this means I get 0 here, and I get 1, and I get 0 here, and these are zeros. Now I'm swapping these two rows. If I swap those two rows, what do I get? I get 1, 0, 1, then 0, 1, 0, then 0, 1, 1, and 0, 0, 0. Okay, what is the, so I can use this second row to eliminate this entry, right? So what do I get? I get 1, 0, 1, 0, 1, 0, 0, 0, 0, which is this. Okay, now, okay, so we have a line of row of zeros, okay? So this is fine. And so this is my free variable, and this is my free variable, but X3 has no free variables. Yes, we can directly deduce it from the first, yeah. So since it's third vector is the first vector plus the second vector, so, but I wanted to do it this way so that we go over this computation again. Okay, so so what is this? We get okay, so we get what I said. So A3 does not have a leading one, so it is free. A2, what is A2? A2 is just 0, right? And what about A1? A1 is minus R because A1 plus A3 is 0. Okay, so we get this solution. So we have infinitely many solutions for this system. A1, A2, A2, A3, which is minus R, 0, and R. So for any R, we get a solution. So we have infinitely many solutions to this system, meaning that the system is linearly dependent. For linear independence, we want only the zero solution. Okay, we want only 0, 0, 0 to be a solution. For this one, I can put, for example, 1. I can choose A1 as minus 1 and A3 as plus 1. Okay, so this means this is non-trivial solution. Non-trivial solutions, maybe, plural, which means the given set of vectors is linearly dependent. Okay, so this is, in a sense, showing that the idea of linear dependence and independence is really looking at the redundant vectors, vectors which do not add new information, okay? So here, two of these vectors is enough to describe this space, okay? Two of them are enough. I can choose either these two, or I can choose these two, I can choose these two, doesn't matter. But one of them is redundant. And here there are no redundant vectors, okay? So this is the idea of linear dependence and independence. And yes, Nesrin, your question is really good. I will say something about it. It's kind of a, is there a theorem like that? I'm looking at it. But it's a general rule. If you can obtain one of the vectors as a linear combination of the others, then that set is obviously not linearly independent because one of them is redundant. It can be obtained by the others. Okay? Okay, so let's do some more examples, okay? Hocam A2 artı A3 eşittir 0 demiştik. Yanlış yazmışım ama. Yok. A2 artı A3 yanlış mı yaptık ya? Burada yanlış yaptık değil mi arkadaşlar? Burada bir 0 var. Ya burada yanlış yapmışız arkadaşlar ya. Okay, let's fix these things, okay? Before moving to the next question. There should be a 1 here, right? There should be a 1. No, there shouldn't be a 1, right? Wait a minute. What did we wrong? So this is correct. What about this line? 1, 0, 1, 0, 1, 1. Then, yeah, this is correct. 1, 1, 1. This looks correct. Okay, then we get a 1 here. But then there's, okay. Yerde bir yanlışlık var mı arkadaşlar? Yok mu? Bir daha bakıyoruz arkadaşlar. I think there's something wrong here. Okay, so this line is correct. So what about this one? A1 plus A3 is 0. A2 plus A3 is 0. A1 plus A2, A3 is 0. So we get these equations. Then what did we do? We get this line. Then we swapped. We get this one. And then we make this 0. We're doing something wrong because I don't want this to be 0. So this is 1, right? So, but now I can make this 0. If I make it 0, I don't get the result I want. Wait a minute. Oh, wait a minute. We did the error somewhere else, guys. I'm very sorry. Okay, I figured out. So I couldn't add these two vectors. So that was my problem. So let's use a different color. So, okay. Okay, so if I add these two vectors, I get a 2 here, right? So this should be 2. So that was my mistake. Let's use green color. So in fact, these three vectors are linearly independent. That's what we showed. Okay, these three vectors are linearly independent, but these three vectors are linearly dependent. Okay, so let's fix everything. Okay, that was a good question. So this should be, there should be a 2 here. Okay, and this should be a 2. And what happens here? What is this thing? So if I swap these, no, I should really, so this should become 1. This should become 1. Okay, everything is good so far. And what about this? I get, now I don't need to swap these two, right? So this line, so I really get, let me fix these things and these things. So these are 1, 1, 0, 0, okay? Now what is the last thing? So this is now in row echelon form. I don't need this line, okay? So I don't need these things. So we have two leading ones, this one and this one, which means A3 is free. A2 is what? A2 is minus R, and A1 is also minus R. Okay. I think now this is correct. So this should be minus R as well, right? No, no. I think I'm making some mistakes here because A1 plus A2 plus A3 must be 0. No, A1 plus A2 plus 2A3 must be 0. This is correct. Okay, now this is limit. Okay, now we fixed that. I'm very sorry. So let's check if it's satisfying all the equations. So A1 plus A3 minus RR is satisfying, minus RR is satisfying, and minus R plus 2R equals 0. Sorry, guys. Okay, so if I take this as 1, you see, if I take this last component as 1, then these vectors are linearly independent. That's what we have shown. And if we take this as 2, sum of the first two vectors, this one, then this is linearly dependent. Okay. Any questions? Any questions? I don't think we have time for another example. So I'm suggesting you, so these are from my lecture notes. I suggest you read these things and try to solve the examples. Okay. Try to do them on your own without looking at the solution. And I have also some exercises from the book. Try to do them as well. So next week we will continue from here. So after this, we have a few more things about section 4. I think next week we may finish section 4. Okay, so yoklama. Arkadaşlar yoklama için ben buradan sistemden çekiyorum. Bir daha buraya yoklama yazmanıza gerek yok bence. Diğer hocalar ama alıyor mu? Öyle mi alıyorlar? Diğer hocalar buraya isminizi yazın diyorlar mı? Evet. Tamam, o zaman gönderin siz de. Okay, everybody write their names. Okay, please write your names. And if you don't have any questions, you can leave the class now.